Hello and welcome back. I'm Matthew Lay, and this is a presentation on resistors to prepare us for lab using resistors. So we have some objectives in this lab. First, we want to understand the color coding system that's on a resistor, and it determines the value that is on that resistor represents. And we want to determine the nominal value. Think nominal is normal value of a 4-band resistor, and also for a 5-band resistor. There's different kinds based on the precision that they hold. And then we want to figure out the tolerance. There is a certain range, even though they may advertise it as a certain value, it would actually still be in what is called tolerance if it's in a specific range. Okay, so what is resistance? We need resistance in every electrical circuit. If not, we have something that we call a short. The circuit is shorted, and you've probably heard that term before. And usually a circuit is protected by a fuse or a circuit breaker, and if it gets shorted or it draws too much current, you're going to pop the fuse or the circuit breaker. The polar opposite of something being shorted is something being open. It has what is said infinite resistance. There is no way that electrons are going to flow because the circuit is open, and I have some examples here to show you. So here's an open. I have a battery and I have a circuit. This right here is depicting a switch, and the switch looks like a door either opening or closing. And of course, if we're looking at this from the top, the door would be open. That means that there is no path for current to flow here, so that is what we call an open. Open switch means no path for current to flow. Now here we have a closed path. Closed path means that we have current to flow, but we actually have no resistance. This is just a wire being connected now with a closed switch from the positive to the negative, which is not good. So we have little to no resistance in this circuit, and the current will increase beyond the output that the battery can handle. So the battery would either get really hot and burn up, or maybe the wire, if it's small enough, would burn up. Something bad would happen. Of course, we would add some overcurrent protection on a regular circuit where we'd have a fuse or a circuit breaker to alleviate this from happening. But this is just a demonstration of what a short would be in a circuit, and that is shorting across the positive and negative of a battery. Okay, so those are our definitions for open and short. Let's look at our resistor color code now. So this is the colors in the spectrum, and each color has a specific numeric value. So if you start with the absence of light or black, and then you start to increase light intensity, the light turns from brown to red to orange, yellow, green, blue. Sometimes they say indigo or violet, but I say purple here, and then gray, and then of course complete bright white light is white. Okay, and that's where we get our numeric values of 0 through 9. 0 meaning darkness, 9 meaning light. And so the order of these sometimes can be hard to remember. So we have a little mnemonic here, and it is better build roof over your garage before Porsche gets wet. Okay, and each letter in the beginning of those words, better build roof over your garage before Porsche gets wet, is the first letter of the color. So B for black, B for brown, R for red, O for orange, Y for yellow, G for green, B for blue, P for Porsche. If you use violet, I guess you could say van gets wet. And G for gray, and W for white. Okay, so on a test, if you have to recite the different colors and their numeric values, you could just say better build roof over your garage before Porsche gets wet, and write that on a piece of paper, and then spell out black, brown, red, orange, yellow, green, blue, purple, gray, and white, and then start numbering them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the resistor bands, there are a certain amount of stripes or bands painted on resistors, and it tells us the numeric value in ohms that that resistor represents. So most resistors use a 4-band color code system. That is probably coming out of vogue a little bit, and maybe the 5-band resistors are getting a little more popular since the manufacturing practices have drawn the costs down. The higher precision resistors are getting cheaper, plus all of our solid state devices that we purchase require tighter balances on all of those things. Precision resistors do have 5 bands on them, and they have their own color code system. The color numbers stay the same. It's just the code and how you read it is a little bit different. Okay, so let's look at a 4-band resistor. The first band will be the first digit in the numeric value, and the second band will be the second digit in the numeric value. And then the third band will be the multiplier, and that's just going to be how many zeros we're going to put behind it. And then the final band is going to give us that tolerance that we're going to have to calculate. And so we'll quantify what tolerance means here in just a moment. Okay, so here is the tolerance band on resistor. The tolerance band has an acceptable range for that resistor that they can fall in, and the resistor is still considered good. The tolerance band is the 4th band on a 4-band resistor. It's the 5th band on the 5-band resistor. So it's always the last band. On a 4-band resistor, you have 3 different possibilities. You have gold, silver, or no band at all. So no band on a 4-band resistor means you'd only have 3 bands, and the absence of one meant that you would have a very poorly manufactured resistor. 20% tolerance is, nobody really even buys those anymore. Back in the old days, maybe. So gold is 5%, silver is 10%, and that's plus or minus, so that's 5% in either direction of the advertised value. And silver would be 10% in either direction, so we're gonna calculate that here. So let's give an example. We're going to go back to that same resistor we were looking at. And here is our color code kind of simplified off to the side. Now this actual list here serves for 4-band and 5-band, and I'll explain why, because we've got a couple extra little color codes there for the tolerance, which I'll explain when we get to the 5-band. So the first band is going to be our first digit of our numeric value, and it is orange. So I come over here and I look, and orange is 3. So 3 means that's our first digit. And then white, if we come down here, we see that white is 9 on our light spectrum. And so it gives us a numeric value. Now remember, the next band is our multiplier. So it is yellow. So that means that's with 4 zeros, or times 10 to the 4th. And then our tolerance band is silver. And you see silver here is plus or minus 10%. For our tolerance band. So the first 2 digits is 39. The yellow on the 3rd band means 4 zeros, or 39 times 10 to the 4th. And that means that that resistor's nominal value, you could replace that with the word normal, or its advertised value, is 390,000 ohms. So we would say that as 390 k ohm resistor. Okay. But it may not measure 390 k ohms. It has a tolerance on it. So let's look at the tolerance here. So we know that the tolerance is 10%. And 10% means we have to multiply that value by 0.10 to find out the value that it could be either positively affected or negatively affected in either direction. So if we take 390,000 times the 0.1, we get 39,000. So then we have to subtract that from our advertised value of 390,000, and we get 351,000. And we also have to add it, because remember, it's plus or minus 10%. So we're going to add to the advertised value of 390,000 to get us 429,000 on the range. So the acceptable range for this is actually 351,000 to 429,000, which we would just say 351 k ohms to 429 k ohms would be the acceptable range. So you see 10% tolerance, it can be quite a wide range of values. And that will have an effect on circuits. So we actually have precision resistors, which we'll talk about here in just a minute. Okay, the third band exception. The third band exception is for very low resistors. These are actually very rare, but they do exist. And the third band is used to move the decimal point over to the left instead of to the right. Okay. And so if the third band, remember gold and silver, I didn't have that listed in that light spectrum because it just goes from black to white. Doesn't include gold and silver. But if the third band contains gold or silver, we're going to actually be moving the decimal point. Instead of adding zeros, we're going to be moving the decimal point on our specific value. We'll see that here in this example. Okay, so now we have silver here in the third band. Okay, so it kind of looks like we have two tolerance bands, but we don't. That's the tolerance band, and this is the modifier. So again, we have orange in the first position, which is 3, and yellow in the next position, which is 4. And we have silver in the third, which means we are going to move that decimal point over 0.01. And then we have a tolerance of plus or minus 10% with the final silver band. So our first two digits together is 34. But since we have silver on the third band, that means times 10 to the negative 2. So we have 0.34 or 340 milliohms. Now see, we took this and we just went 1, 2, 3 over. And that's why we have 340. We had to move in groups of 3 to make it engineering notation. And since we moved it group of 3 to the right, we have to use a milli to move it to 3 to the left again to get the proper quantity. Okay, let's look at 5 bands. 5 bands have an extra band for the numeric value, and so we can be a little more precise. So the first digit, second digit, and third digit are the first 3 positions, and then the fourth I'm saying digit, a fourth band is going to be our multiplier, and then always the last band is going to be our tolerance. Okay, so that's the first band is going to be our first digit, second band, second digit, third band is the third digit, and then the fourth band is our multiplier. Okay, so we're going to look at this. We have, again, orange for 3. We have that twice. Then we have white as our third band, so we have 339. And now some students, I specifically put this in here because some students get confused. They think, oh, and then I have 1 0 on the end of that. No, I have 0 zeros. So that multiplier is times 10 to the 0. And then there is our tolerance. So we have 339 for our 3 digits. And the fourth band have 0 is 339 times 10 to the 0th power, which is the same thing as times 1, because any number to the 0th power is 1. So we're not going to put any zeros on the end of this. So we're just going to have 339 ohms for this resistor. And I'll tell you now, it is a little confusing, and a lot of students will say 3,390 ohms because this is black, and black has a value of 0. But remember, that's 0 zeros, or 10 to the 0th power. Okay, so let's look at the tolerance of the fifth band. I said these are precision resistors, and so we actually get a couple more colors for our tolerance. Okay, so this fifth band is our tolerance, and so we have plus or minus 1% if we have a brown stripe, a brown band in that tolerance location. We have plus or minus 2% if it's red, and then gold and silver stay the same. Okay, so and there is no absence of a band in this case because these are precision resistors. Okay, so here we on our tolerance band have a brown stripe, so it's plus or minus 1%, and 1% is also 0.01 in decimal form. So we're going to take our 339 ohms times 0.01, and that gets us 3.39 ohms. And of course, that's plus or minus, so we're going to have to subtract it and add it. So 339 minus 3.39 ohms is 336.61 ohms. And 339 plus 3.39 is our 342.38 ohms. Okay, so our acceptable range is 336.61 to 342.38 ohms. Okay, so a little more precise there. It's a lot closer range, and it can be used in more precise circuits. Okay, so let's review. Understand the color code system that is used to distinguish the value of the resistors. So if you want to pause, see if you can come up with that mnemonic on your own and write down on a piece of paper the values that each color represents. Okay. So our mnemonic is better build roof over your garage before Porsche gets wet. Okay, so the B is for black, and B is for brown in that order. R is for red, O is for orange, Y is for yellow, G is for green, B is for blue, P is purple, G is gray, and W is for white. Okay, so and then those are just numerically from the top to bottom: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Determine the nominal value of a 4-band resistor. So I'm going to give you this resistor. So take a look. We have brown, black, yellow, and gold. Okay. So if you want to pause the video, try to figure that out, and then come back. Okay, so the first digit's red, that's 2. Second digit is black, that's 0. Third digit is band. Third band is yellow, and the fourth band is gold. So the first 2 digits is 20, and the multiplier is 4, so we're going to put 4 more zeros behind that. So that'll give us 200,000 ohms, or 200k ohms is our actual value. Okay, let's continue our review. We're going to determine the nominal value of a 5-band resistor. So here is a 5-band resistor, which is brown, black, black, orange, brown. So if you want to pause the video, calculate that out, and then come back. Okay, the first digit is brown. The first band is brown, which means a decimal value of 1. The second band is black, which gives us a 0, a significant digit of 0. The third band, which represents the third digit, is also black, so that gives us a significant digit of 0. And then the fourth, which is a orange band, is a multiplier, and that's going to add 3 more zeros, or place 3 more zeros onto the end. And then our tolerance band is 1%. So the first 3 digits, which are significant, is 100, and then the fourth band means we're going to have 3 more zeros on there. So we're going to have 100,000 ohms, or 100k ohm resistor. Now we want to determine the allowable tolerance for a given resistor, okay? So we have the same resistor here. So we know that the tolerance is plus or minus 0.1%, which in decimal form is 0.01. And we just calculated out that that was a 100,000 ohm resistor times our 0.01. It's going to move the decimal point over 2 to the left. So that's why we have 1,000 ohm plus or minus tolerance. So we subtract it first and we get 99,000 ohms for one end of the range, and we add it and we get 101,000 ohms for the other end of the range. So the acceptable range can be said to be 99 to 101 k ohms. Okay, we didn't talk about this in the earlier, but I just placed this in here. This is an actual symbol for a resistor, and resistance is the opposition to current flow. And if you imagine this is like a water pipe, and the water would have to go through all those bends, it would slow the water down. That's what the symbol's trying to show. It's trying to show that we're basically a wiggly part of the road for the electrons moving along in this circuit. So that is our symbol for a resistor. And typically we just put the value of the resistor either to the bottom or to the right of the resistor when it's in our drawings. So that concludes our presentation on Resistor Lab. I hope that was helpful, and we'll see you in the next video.